Welcome to the lecture series of signals and systems. In the previous lecture, we have seen the foundation for the jet transform. We have seen how we can find the jet transform even for those signals for which the DTFT means discrete time Fourier transform is not possible. Means the signals which are not absolutely summable, for them also we can find the jet transform. So we know the region of convergence definition for the region of convergence in the Laplace transform, which says that the region of convergence is the value of those values of sigma for which the Laplace transform can exist. Similarly, in the Z domain, what we have seen is, so this is S plane, this is sigma, and here it is J. This is the S plane in the Laplace transform. Similarly, we can find the region of convergence for the Z transform also. What we have seen earlier is the variable Z in the Z transform is equal to R into e power j omega. So, what will be the modulus of this Z? This will be equal to R. And we know from the discussion that this R is equal to e power sigma, where sigma is the real part of this variable S. So, if we want to plot the ROC for the Z transform, means real part of Z with respect to imaginary Z. So this is real Z and this is imaginary part of Z. This mod of Z will be equal to a circle of radius R, and this R will be, suppose this when sigma is equal to 0, then this R will be equal to 1. Means for sigma equal to 0 means origin of S plane, in the Z plane it will be a circle of radius 1. So this is the sigma equal to 0 in the S plane and R equal to 1 in the Z plane. Radius of this circle is 1 and it is drawn for sigma equal to 0. Now, if we move to the left side of this origin, means when I will put negative values of the sigma, suppose I am putting here sigma equal to -1, then this R will be equal to e power -1, or it can be written as 1 upon e, and this 1 upon e is definitely, it is less than 1. It means that as we move to the left side of this j omega axis in the S plane, in the Z plane we will move inside the circle. Means when this sigma equal to -1, when sigma will be equal to -1 in the S plane, then here Z will be less than, will be a circle of radius less than 1. So for sigma is equal to -1, it will be a circle like this, whose radius is equal to, this is for sigma equal to -1, when its radius is 1 upon e. Now, if we go to the extreme left of the S plane, means when I will put sigma equal to -infinite, then this R will be equal to e power -infinite, which is equal to 0. Means the sigma equal to 0 point will be mapped to a circle of radius equal to 1. Sigma equal to -1 will be mapped to a circle having radius less than 1, and sigma equal to -infinite will be at the origin of the Z plane. means r equal to 0, a circle of radius 0. This is what sigma equal to minus infinite. Now if I will move to the right of this S plane, means suppose I put sigma equal to 1 here, then r will be equal to e, which is obviously it is greater than 1. Now the if we move to the right side of the S plane, then it will result in a circle having radius greater than 1. So this is sigma equal to cos sigma equal to 1 and its radius have magnitude equal to r equal to e. Now if I will move extreme right to this S plane, means when I will put sigma equal to infinite here, this r will be equal to e power infinite, which is equal to infinite. Means when I will move to the extreme right of this S plane, it will result in a circle of radius infinite in the Z plane. So from this discussion, I can map the S plane into the Z plane by the following conclusions. The conclusion is the left of the S plane is mapped inside a circle of radius 1. The left, I will repeat again, the left half of the S plane is mapped into a circle having radius 1, and the right side of this S plane is mapped to a circle having radius greater than 1. Means when I will move from sigma equal to 0 to sigma equal to infinite, here I will move from r equal to 1 to r equal to infinite when I will move to the right side. When I will move to the left side of this plane, when I will move from sigma equal to 0 to sigma equal to minus infinite, in correspondence to this, in the Z plane, we will move from r equal to 1 to r equal to 0. This is how the S plane of the Laplace transform can be mapped to the Z plane of the Z transform. Now we will discuss some important questions and their ROCs. We will find Z transform of some useful functions and then we will discuss their ROCs. So the given example here is, suppose x of n, a discrete time sequence x of n is given as n into delta n. For this function, we have to find the Z transform. We know the relation to get the Z transform, that x of z is equal to sigma n is from minus infinite to plus infinite x of n into z power minus n. Here x of n is given as n into delta n. So I will put this value here. This will be equal to sigma n is from minus infinite to plus infinite n into delta n into z power minus n. Or we can break this limit as equal to sigma n is from minus infinite to minus 1 n into delta n into z power minus n plus sigma n from 0 to infinite n into delta n into z power minus n. This is from minus infinite to minus 1, so because this is a summation, we can put it from minus 1 to minus infinite also. N is from minus 1 to minus infinite. That doesn't matter. So now solve these two summations. When I will put n equal to minus 1 here, this will become minus del of minus n minus del of minus 1 into z power 1 plus, instead of plus, because I am taking only negative values of n, so this will be minus. When I will put n equal to 2, this will become del of minus 2 z square plus, this is again minus 3 del of minus 3, and this is z cube plus, it will go to the infinite. This is for this first summation. This sequence is for this given summation when limit is from minus 1 to minus infinite. Now put this summation as this is, when I will put n equal to 0, the summation will become 0. When I will put n equal to 1, then this will become del of 1 into z power minus 1 plus, when I will put n equal to 2, this will become 2 into del of 2 into z power minus 2 plus 3 into del of 3 into z of minus 2. So this will be, this sequence will look like this after putting the values of n from minus infinite to 1, minus 1, and also from 0 to infinite. Now here this is del of minus 1, this is del of minus 2. Similarly, this is del of minus 3 and z cube. Here it is del of 1, del of 2 and del of 3. All these values, delta of delta will become, simply these values will become 0, because delta function will give value only at delta equal to 0. Delta 0 will be 1. All the other values of delta, for all the other values of n, this delta function will become 0. It means that this will become 0, this will become 0, this will become 0. Similarly, all the values, because delta is involved here, these values will become 0. Only one term is there, which is 0 into delta 0. Here the value of delta 0 is 1, but because it is multiplied by n and value of n here is 0, it will become 0 also. It means that the z transform of the given signal, z transform of the given sequence n into delta n will be equal to 0, and this is for all the values of z. Value of z doesn't matter here. Whatever is the value of z, this sequence is going to be 0 because of this delta function. So it means that this will happen for all values of z. It means that ROC, its ROC is all z. This is for all values of z, because this sequence is not dependent over values of z. It is going to become 0 because of delta of n. Now consider another example in which x of n is given as delta m minus 4. The next example says that the sequence is given as x of n is given as delta n minus 4. For this sequence, we have to get the z transform, and we know the formula to get the z transform as x of z is given as sigma n is from minus infinite to plus infinite x of n into z power minus. Here x of n is given as delta n minus 4 into z power minus 1. Again, this is impulse function, and this impulse function, this delta n minus 4 will be equal to 1, while this delta n minus 4 will be equal to 0, when this n minus 4 will be equal to 0, and this will be 0 when n minus 4 is not equal to 0, means except n minus 4 equal to 0, for the other values of n minus 4 this delta will be equal to 0, and this will be equal to 1 when this n minus 4 will be equal to 0, means when n will be equal to 4, only then this delta n minus 4 will be equal to 1, otherwise it will become 0. So it means that this will give z power minus 1, but when n is equal to 4, it means that this will become z power minus this will become z power minus 4. Again, this is for all values of z. Z can take any value except z equal to 0, because this is equal to 1 upon z power 4. So mod of z cannot become 0. The next example is x of n is given here as n into delta n minus 2. X of n is equal to n times delta n minus 2. Again, we can write it as its Z transform can be written as sigma minus from minus infinite to plus infinite x of n to z power minus n. Or we can write in place of x of n, we can write n into delta n minus 2, that is from minus infinite to plus infinite to z power minus n. Again, this impulse function will be equal to 1, value of this delta of n minus 2 will be equal to 1 when n minus 2 will be equal to 0. This implies that when n will be equal to 2, otherwise this will be equal to 0. So we can find the value of this delta function only at n equal to 2. For the other values of n, the value of this function delta n minus 2 will be equal to 0. So only one value of n is there, for which this summation will give some value, otherwise this will be equal to 0. So I will put n equal to 2 in this summation and will get the result. So this will be equal to 2 times n into 2 minus 2 into z power minus 2. So this will become 1. This will be equal to 2 into z power minus 2. This is what we will get by applying the relation of z transform. The next question is yn is given as here value of n is given as x of n minus 1 into u of n. Now put this given function in the formula for the z transform, which is equal to x of z is equal to sigma n is from minus infinite to plus infinite x of n into z power minus n. And because we had to get the z transform of this yn, I will put value of this yn in the given relation, and this will become sigma n is from minus infinite to plus infinite x of n minus 1 union z power minus n. Because the power n is given here, this u of n will exist only for the positive values of n. For the negative values of n, this u will be equal to 0. So I will put limit here from 0 to infinite, and from 0 to infinite x of n minus 1 to z power minus n. If somehow I will get x of n here, then this will become x of z. But it is given here, instead of x of n here, it is given x of n minus 1. So I will consider this variable. Suppose n minus 1 is equal to k, then n will be equal to 1 plus k, and limit of the k when this n will be equal to 0. When this n will be equal to 0, then k will be equal to minus 1. And when this n will be equal to plus infinite, this will be equal to, this k will be equal to infinite. So the limit here will become, now this x of z will be equal to sigma. Now limit will become from k is equal to minus 1 to k equal to infinite, and this will become x of k into z power minus n. Instead of n, I will put here 1 plus k, and this will become sigma k is from minus infinite to plus infinite x of k into z power minus 1 into z power minus k. This z power minus 1 is a constant here, so I will put it outside of the summation, and this will become n is from minus infinite to plus infinite. This is 1 and limit is on the k here, so this will become k from minus 1 to plus infinite x of k z power minus k, x of k z power minus k into z power minus 1. So if the limit is from k equal to 0 to infinite here, then this will become x of z. When limit is from 0 to infinite, this will become x of z. But one extra term is here, which is at k equal to minus 1. This term is extra, so I can write it as z power minus 1 into sigma. I will put k from 0 to infinite x of k z power minus k. But I removed k equal to minus 1 here. Then it means that we have to add this term at k equal to minus a, and at k equal to minus a, this will become x of minus 1 into z power 1. I will put k equal to minus 1, this will become z power 1. Now this term k from 0 to infinite x of k into z power minus k is same as this relation, and from 0 to infinite, or we can say the formula of z transform, x of n into z power minus 1. Here it is x of k into z power minus k. It is the z transform of k, so this can be written as x of z. This can be written as x of z, and so this will become equal to z inverse into x of z plus x of minus 1 into z power 0. And this can be further simplified as z inverse x of z plus z inverse x of z plus x of minus 1. This is the way to represent the z transform of the given system. Now consider another similar example. In which y of n is given as x of n plus 1 into u. Y of n is given as x of n plus 1 into u of n. This is the function, this is the given sequence for which we have to get the z transform. And we know that the z transform for this function y n can be given as sigma y of n into z power minus n, or this can be convergence here from minus infinite to plus infinite, and further we can put the value of y of n here, which is equal to n from minus infinite to plus infinite x of n plus 1 into u of n into z of minus n. Again, because n is given here and this will exist only for the positive values of n, so we'll remove the negative values of n from this summation, and this will become sigma n is from 0 to infinite x of n plus 1 into z of minus n. Again, we need here x power n into z power minus n, so that this will become x of z. For that, I will put n plus 1 equal to another variable p here, and from here n will be equal to k minus 1. And what will be the limit? When I will put n equal to 0, then k will be equal to 1. When I will put n equal to infinite, then k will be equal to plus 1. So the new limit here will become this y of z will be equal to sigma k from 1 to infinite, k is from plus 1 to infinite x of k into z power minus k minus 1. In place of n, I will put here z power k minus 1. Now this will become sigma k is from 1 to infinite x of k into z power minus k into z power plus 1. Again, then z power plus 1 here, it is a constant. I will put it outside of the summation. So this will become z power 1 sigma k is from 1 to infinite, k is from 1 to infinite x of k into z power minus k. Again, here limit is from 1 to infinite. If this limit will become from 0 to infinite, this will become x of z. For that purpose, we have to add an extra term for k equal to 0, because we have to include in this term also, term for the k equal to 0, and similarly we have to subtract this term also. So I will add one term k equal to 0. This will become z power 1 into sigma k is from 1 to infinite x of k into z power minus k, plus I will add an extra term for k equal to 0. So this will become x of 0 into z power 0 minus x of 0 into z power 0. Now, after adding this x equal to 0 here, after adding k equal to 0 here, this will become equal to sigma. After including this term for k equal to 0, I will put this limit from k from 0 to infinite instead of k from 1 to infinite, because k equal to 0 is also added here. So this limit will become from k equal to 0 to k equal to infinite x of k into z of minus k. Now one extra term is there, minus x of 0. Again this will become x of z. So this can be written as further simplified as z into x of z plus, not plus, this is minus x of 0 z. This is z into x of z minus x of 0 into z. This is what we will get from the z transform of this. So this is all for this lecture. In the coming lectures, we will include some more examples and clarify the concept of region of convergence of the Z transform. Then we will move to discuss the properties of the Z transform, and we will discuss the examples based on the properties of the Z transform. So this is all for this lecture.